In the vastness of space, a cosmic ballet unfolds, one that will end in destruction, transformation, and the birth of something entirely new. Meet the red giant, a dying star hundreds of times larger than our Sun, its bloated atmosphere reaching far into space as it nears the end of its life. But this red giant isn't alone. Hurtling through space at incredible speeds is one of the universe's deadliest objects, a neutron star. Neutron stars are nature's densest surviving stars. Just a teaspoon of neutron star material would weigh as much as Mount Everest. Their gravity is so intense that even light struggles to escape their surface. The size difference is staggering. While the red giant spans millions of miles, the neutron star is barely the size of a city. But what it lacks in size, it makes up for in raw gravitational power. As these two celestial bodies draw closer, the neutron star's immense gravity begins to tear at the red giant's outer layers. First, wisps of the giant's atmosphere are pulled away, forming brilliant streams of gas that spiral toward the neutron star like cosmic waterfalls. What happens next defies our normal understanding of stellar physics. The neutron star pierces the red giant's outer layers like a bullet through silk. But instead of emerging on the other side, it begins to burrow deeper, drawn inexorably toward the giant's core. As it plunges deeper, temperatures soar to millions of degrees. The neutron star's path creates a tunnel of superheated plasma, setting the stage for one of the most bizarre transformations in astronomical science. As the neutron star reaches the red giant's core, it begins a process that will forever change both stars, creating something entirely new in our cosmic cookbook. The neutron star doesn't simply sit in the core. Its intense gravitational field acts like a cosmic blender, violently stirring the giant's internal layers. Elements that normally never mix are suddenly forced together in a chaotic dance. Helium, carbon, and oxygen from different layers of the red giant are dragged into new configurations. The neutron star's motion creates powerful currents in the stellar material, similar to how a boat's propeller churns up water. The temperature at the mixing zone reaches unimaginable levels, far hotter than the core of our Sun. The friction and compression from this mixing generates temperatures exceeding 1 billion degrees. At these temperatures, entirely new nuclear reactions become possible. What emerges is neither neutron star nor red giant, but something unprecedented, a hybrid star with properties of both parents. The hybrid star combines the crushing density of a neutron star with the expansive envelope of a red giant. Its structure defies conventional stellar models, creating a cosmic laboratory for extreme physics. The interior of this stellar hybrid contains regions of drastically different temperatures and densities. Normally, stable layers become turbulent zones where elements transmute into one another through exotic nuclear reactions. But this extraordinary cosmic merger exists in a state of constant change, evolving faster than any normal star. The hybrid star is unstable, changing more in a few years than our Sun does in millions. It ejects shells of material into space, while its core continues its violent mixing, setting the stage for even more dramatic transformations. Deep within the hybrid star, conditions exist that can't be found anywhere else in the universe. Here, atomic nuclei are about to undergo transformations that would make ancient alchemists envious. The crushing gravity of the neutron star compresses material to densities millions of times greater than Earth's core. At these pressures, atomic nuclei are squeezed so close together they nearly touch. The temperature in this cosmic crucible ranges from millions to billions of degrees. Different shells within the core become specialized factories, each producing its own unique mix of elements. But it's not just heat and pressure that make this place special. The neutron star provides something crucial: a vast supply of free neutrons. These free neutrons bombard existing atomic nuclei like a cosmic shotgun. Each hit adds another neutron, building heavier and heavier elements in seconds, rather than the millions of years it would take in normal stars. This process, called rapid neutron capture, creates elements far heavier than iron. Gold, platinum, and uranium are forged in these extreme conditions, along with elements so rare they don't exist naturally on Earth. The hybrid star pushes the boundaries of nuclear physics, creating elements that stretch the limits of the periodic table. Many of these newly forged elements are highly unstable. They decay rapidly, releasing enormous amounts of energy and transforming into other elements in a cosmic game of atomic musical chairs. And here's where things get really interesting for our own existence. These rare elements don't stay trapped in the hybrid star forever. The hybrid star ejects huge clouds of these rare elements into space. This enriched material will eventually find its way into new stars, planets, and yes, even living things. The gold in your jewelry might have been forged in one of these cosmic crucibles billions of years ago. For centuries, astronomers thought they understood how stars lived and died. Then we discovered these hybrid stars, and everything changed. Traditional stellar evolution follows predictable paths. Stars are born, live by fusing elements in their cores, and die in specific ways based on their mass. But hybrid stars throw this entire rulebook out the window. First, these stars violate our understanding of stellar structure. Their cores aren't neatly layered like other stars. Instead, they're more like a turbulent ocean, with material moving in ways our computer models never predicted. By all normal physics calculations, these stars shouldn't even exist. The forces involved should tear them apart instantly. Yet somehow, they find stability in chaos. The neutron stars' intense magnetic fields interact with the swirling stellar material to create previously unknown forms of stellar equilibrium. These stars also break the rules of energy generation. While normal stars produce energy primarily through fusion in their cores, hybrid stars generate energy through a complex mix of fusion, friction, and gravitational effects throughout their entire structure. Perhaps most bizarrely, hybrid stars seem to ignore the normal rules of stellar aging. A normal star might take millions of years to show significant changes, but hybrid stars can transform dramatically in just decades, cycling through multiple stellar lifetimes worth of evolution in the blink of a cosmic eye. These discoveries are forcing astronomers to fundamentally rethink some of our most basic assumptions about stellar physics. Our best computer models, which can accurately simulate normal stars, completely fail when trying to predict hybrid star behavior. It's like trying to forecast weather with only half the equations. But in these failures, we're finding surprising new insights about how stars really work. We're discovering that processes we thought were independent are actually deeply connected. Magnetic fields influence nuclear reactions. Rotation affects element mixing. Everything is more intertwined than we ever imagined.